Hey Senior Math, it is Mr. Canfield. I promised I was going to go over this review packet and stuff got away from me, so here's a video for anybody who needs it. I normally use Desmos or my phone calculator. I don't have one of them, but I have one of these. So here we go. All right. In a study of how college education costs have changed since 1980, each year's average cost of tuition is expressed as a percentage of the 1980 cost. Which term refers to the 1980 cost? So we're basing everything off of it. That's called our reference value. We're referencing it. A rate of inflation, that would be some percent we were calculating between two things. Price index, that's, again, it's going to be something where we use this to find it. Okay, what is the primary purpose of index numbers? So is it for predicting the future? Is it for measuring the strength of the economy? Is it for determining interest rates, or is it to facilitate comparisons? The main thing with index numbers is we use them to compare different things. Who computes and reports consumer price index? We talked about this in class. It was a bureau, not this one, the Bureau of Labor and Statistics. So, all right. I don't know exactly what I was saying before someone knocked on my door. That's okay. Which price index measures consumer attitudes so that a business can get... So the CPI is what I thought this was going to be, but it talks about consumer attitudes. We have not talked about this, but it's called the Consumer Confidence Index. And if I was taking a test and I wasn't sure of the answer, I can see consumer attitudes. It's focusing on attitudes. So confidence and attitudes have similarity there. So that's a context clue for us why that would be the right answer. If anything like that shows up on our test that I didn't end up teaching, do your best on it, and it's probably one of those where I will curve it out of the actual test. All right, now into stuff where we might actually have to do some calculations. Let's see. The following table provides information about regular gasoline prices in the U.S. by region. So we've got like East Coast, Midwest, Gulf Coast, Rocky. These are different parts of the country, and these are, looks like, average gas prices. Use this information to answer questions 5 through 7. So remember, when we're talking about price index, the idea is there's some baseline price that we're comparing everything to, right? That was our reference value from earlier. So in this case, the base value is worth 100%. So I already know East Coast is going to be my price that I'm indexing everything else off of. This 98.9%, that's of my East Coast. So I already know Midwest is going to be a little bit less, and sure enough, we can see it's a little bit less. So calculate the price index for the Gulf Coast to complete the table. Well, we know that 3.495 is the 100%. So if I want to calculate the Gulf Coast, that is 3.231. So we just take that and divide it by our reference value of 3.495. Let's see, 3.231 divided by 3.495. So I got 0.924, and so we're going to turn that into a percent. So we'll move the decimal place over, or multiply by 100 is the, what we're actually doing. So 92.4%, and that is right there. Just a heads up, I have the answer key pulled up in front of me as well. I just want to, I don't know, I make silly mistakes all the time, so I'm just trying to stop myself from making any silly mistakes. Given that the retail gasoline price for the West Coast during the same week is 3.866, calculate the price index for Gulf Coast using West Coast as the reference. Oh, this time it's saying use this as reference value. So instead of doing 3.231 over our that one, we'll do our Gulf Coast over this new number, 3.866. So I'm getting oh, right, I forgot this is a solar powered calculator, so if I cover it up, that goes away. Sorry. All right, so 8357. So it's going to be 83.57. It always just moves the decimal place twice. You don't actually need to use your calculator to do that. 83.57. All right, so, 83.6. All right. So we're a quarter done-ish. All right. If it cost you $40.92 to fill up your tank in Iowa, Midwest, how much would it cost you to fill up the same tank in Rocky Mountains? So 40.92 in Midwest. All right. 40.92 in Midwest. So we're going to want to scale this, right? If it's 40.92 in the Midwest, and then we're interested about Rocky Mountains, so we could set up a proportion here, right? We could say, well, 40.92 goes to 98.9. And is this what we're doing? No, hold on. Let me read the question again. If it costs you this much to fill up your tank here, how much would it cost you to fill up this? Oh. I need to figure out how many gallons I used. Sorry, I'm overthinking that. How many gallons did we use to get that? Well, we know it's that much per gallon, right? So 40.92, that's our money. Just divide that by the price per gallon. 3.456. That's how many gallons we used, right? So I used 11.84 gallons. In the Rocky Mountains, it costs that much, right? So in the Rocky Mountains, all I have to do is, that's how many gallons I'm filling up. Multiply this by my price in the Rocky Mountains. So I got $42. .45. So, I just want to remind you that when I do these, I always try to do them in an intuitive way, trying to figure things out instead of what is some formula. So I know I started going to that proportion thing, and that may have actually worked, but I was like, hold on, let me just figure this out. So, given that the consumer price index was 82.4 in 1980 and 215 in 2008, find the price in 2008 dollars of a car that used to cost, of a used car that cost $1,500 in 1980. So, wow, how much does that go up? So we went from an 82 to a 215. So, how much more percent are we getting here? So if we take our 82.4, that's 1980, and wait, we want to start, sorry, so that's our baseline, right? We're starting with our baseline. So if we want to see how much we scaled up by, how much we inflated by, so 2.61 times, that's 2.61 times bigger. So if I make that much bigger of our 1,500, then I get 3,000, this one. So if you do want another way to figure these out without just kind of doing it all in the calculator like this, we can say, well, if I compare 82.4 and 215.3, that should give me the same comparison that I get when I compare $1,500 and the price in 2008. So it should be relatively the same. So what we do is, well, the 1,500 was our 1980, which that was up here. So I can put 1,500 here, and then I can put an X here. And you can cross multiply and get 82.4x is equal to, like, it's solving a proportion. I would imagine you've done these before. So we got all that, and I'll divide it by 82.4. So this is an alternative way to get there. Like, we multiply that, and then, oh, what number did I get? I got a big number here, and then I divided it by 82.4. So that's a more algebraic way to do it. Let's see. Given that the price index was 215.3 here and 214.5 here, find the rate of deflation. So we are looking to see how much it shrunk. So a reference value, we're doing 2008 to 2009. So what is that, just 215.3 over 214.5? 215.3 divided by 214.5. So change that to a percent. It's 100.37%. So we're losing 0.37%. All right. The consumer price index was 179.9 in 2002 and 240 in 2016. If a person earned $59,500 in 2002, how much did he earn in 2016 to maintain the same standard of living? So again, we can just figure out what this is scaling up by and scale our money by that. So 179 to 240. And we're starting with a base number in 2002. So I'm going to do my 240 divided by 179.9. And we'll scale up that. We can use that to scale up our 59,000. So I got 79,377. Let's get that one. And with that, again, if you want to handle this an alternative way, we can say, well, I know 179.9 compares to 240, and that should follow the same suit as this 59.5, and that was in 2002, so 59.5. And then our unknown there, and cross multiply, and then divide, and it'll give you the same thing. All right. Next. A television producer tested her theory that watching her new television program improves a child's reading ability. She designed a reading test and gave it to 500 children. She collected the information in the table. So there's 500 kids here. Some of them passed the test, some of them failed the test. Some of them watched the program, and some of them did not watch the program. It says, what percentage of the 250 children who did not watch the program, so we're looking at the bottom row there, we're looking at the 400, or the 46 and the 204. What percent of them failed the test? 204 of them failed the test, and there were 250 of them total. So percentage is 204 out of 250. So move it over 2 spaces, you got 81.6%. Whoa, oops. So this was our failed. I didn't read this right. It says what percent passed and what percent failed. So the 81.6 that's the second number. Oh, I'm already done then by accident. Nope. I totally biffed it. I did not read this well. All right, sorry about that. What percentage of the 250 children who did not watch the program passed the test? So we're looking at the did not watches and passed. So we're looking at 46 of them out of 250. So that's 18.4%. So our first number is 18.4%. But so what I did was I stopped reading and I picked up, like I mushed the sentences together. That's the answer to the first part. What percentage of the 250 children who watched the program, those are the yes watchers, that's these ones, failed the test? So that would be 87 out of 100. Nope, man, I always do that. We want the failed watchers. Well, there were 250 watchers total. We don't just take these two numbers and run, we do part over whole. 7 out of 250. So I get 34.8%, which is that second number there. Okay. So I hope my screwing up here emphasizes the importance to read slowly and focus on just a part of it and not try to just do everything all at once. Okay, number 2, which of the following claims is best supported by the data in the table? The program has no effect on a child's reading ability. Well, let's see. More kids passed it. Like both of these groups were 250 kids. And if you watch the program, a lot more people passed it. So I'm going to say no. Sometimes we could, so it seems like you do better if you watch the program. So I think B looks like it's probably our answer, but with a question like this, I'm going to read all the answer choices. The program hinders a child's reading ability. Well, then we would expect to see 46 and 204. We would expect to see a worse result here, so I don't see that. The program develops a child's sense of community. This is unrelated. So that's not going to be it. So yeah, B is the clear answer. All right. The 300 children in the study about the correlation between watching a television program and reading ability can be split into 2 groups according to age. Oh, so this is from the same study from before. The results break down as indicated in the following table. So here are the 5-year-olds. So 5-year-olds, a lot of failures. Oh, you know what? A lot of failures here too. For 5-year-olds, what percentage of the 50 children who watched the program passed the test? 50 children who watched the program. These are 5-year-olds who watched the program, these 50 kids right here. What percentage of the 100 children, nope, I did it again. What percentage of 50 children who watched the program passed the test? 7 passed. So 7 out of 50. I'm pretty sure I know what that is off the top of my head. Anytime you're doing something out of 50, yeah, you just double the number and that's the percent. So that's 14%. Oh, I'm done the question then. So anytime I'm doing a multiple choice test and I have 2 numbers, if I get the first one, it's really important that I check the second one. Because if I hadn't done that, I made a mistake on this previous question, and that would have That would have hurt me. So I should still do the rest of the question. What percent of the 100 children who do not watch the program pass the test? So 5-year-olds still, these 100. So 23 pass the test out of the 100. Oh, that's 23%. So now both my numbers match up. So I'm less likely to have made a silly mistake. Now we're looking at 7-year-olds. What percent of the 100 children who watch the program? Oh, 100 children who watch the program. Oh, cool. So I don't even have to like do any math. It's just 35% and 65%. So percent who watched passed, 35% watched and passed. So that's either it's one of those. And what percent of the 50 kids who don't watch pass? That's 18 kids, but remember we double that to 36. So So 35 and 18, nope, but 35 and 36, yes. So what describes the results there? So if you got this one wrong, that's gonna change your answer down here, and I'm gonna have to make sure I account for that. All right, so we can see that all right, within each age group, children who watch the program read much better than children who do not watch the program. Well, in this one, those kids actually did better and they didn't watch the program, so we can't say that. Within each age group, children who do not watch the program read much better than the children who watch the program. Well, our percent here in the 7-year-olds, it's not much different. Within each age group, children who watch the program do better on the test, but the difference is minor. Well, in this one it was 14 and 23. So this was watch, this was do not watch. This was watch, this was do not watch. The do not watches did better in both cases. But it's not a huge difference, it's just minor. Okay. Consider the results from each age group as well as the results within the age groups combined. Which of the following most likely causes Simpson's paradox? So, I already said in class that I wasn't going to be testing on Simpson's paradox, but depending on how, so we took this data and then we broke it apart and looked at it differently, and it gave us different results essentially. And so if we look at our answer choices here, the children who watch the program are mostly 7-year-olds whose reading skills would be expected to be further developed, while the children who do not watch the program are mostly 5-year-olds whose reading skills would be less developed. So there is this like outside influence, kind of a failure of how this is broken down and studied. And if we're just looking at raw numbers, we might not realize it. So that's the correct answer here, but again, I'm not going to be including Simpson's paradox on the real thing. This was just, I needed to get this together as fast as I could. All right, last little bit of questions. Suppose that a colon cancer test is 97% accurate. It will correctly detect 97% of the patients who have colon cancer, and it will correctly identify 90% of the patients who do not have colon cancer. Of 1,500 patients who took the test, 79 tested positive for colon cancer, while only 50 actually have colon cancer. Here's the data. What percent of patients with colon cancer tested negative? So, has cancer but tested negative. So that is a 1 out of how many? Total of 50. So if we do that calculation, that is 2%. What percentage of patients who tested positive do not have colon cancer? So let's look at how many people tested positive. 79 people tested positive. 30 of them did not have cancer. So that's 30 out of the 79. So it's about 37.9%, so 38%. What percentage of patients who do not have colon cancer tested positive? Percentage of do not have. So do not have, that's 1450. So, all right. Do not have colon cancer. So that's here. There's 1450 of them. How many of them tested positive? 30 of them. So that's 30 out of 1450. So that's 2%. So all right. So in both of these cases, 7 and 9, just to be instructive for a second, very small amount of people, when they're taking these tests, they get the wrong result. This is the wrong result. They actually had cancer and they tested negative. They didn't have cancer and they tested positive. Like they actually, so that's a very small percentage. So, and then this right here, percentage of patients who tested positive but don't actually have it. So if we look at the positive tests, you actually are much more likely to test positive and not actually have it, which if this was reversed, I think it'd be a lot scarier. But false positives are like, okay, oh no, it like puts us on high alert, and that's terrible. We would hate to be on high alert for no reason. So 38% of the people who test positive essentially test positive for no reason. But you can go through and begin treatment and look at things, and we would rather, I'm just guessing here, we would rather, you know, this is erring on the side of caution essentially, while you're less likely to miss it. Okay. And I'm sorry if you or a loved one has gone through the cancer battle. My mom's gone through it in the last couple of years. It's not fun. All right. 2 candidates for governor of a state differ in their accounts of the state's economy during the incumbent's term. The incumbent claims that during his 4-year term, the economy has improved, citing a rise in the median household income from $33,000 to $34,500. The challenger claims the economy's declined, citing the buying power of families in the state has declined during the 4 years. Which of the following best explains how both candidates can be right? Hey, people are earning more money than they used to. Yeah, but they can't afford as much as they used to. So, easy one to get rid of. It is not possible for both candidates to be right. One of them is obviously lying. That's a really silly thing to say. All right. Candidates always tell the truth by nature. That is also a really silly thing to say. Though the median household income increased, prices increased by a greater percent, meaning the greater income buys less goods and services. So that sounds very believable to me. That I believe that's the situation that we're in right now. I'm making more money than I've ever made, and I feel like I can barely afford what I used to be able to afford on less money. The incumbent is referring to the economy within the state, while the challenger is referring to the national economy. Well, we didn't hear either of those mentioned, so that's not correct. So, all right. I hope this was helpful. oh wow, under half an hour right now. Bye.